Welcome back, class. Good to be with you. We're going to do Whitlock and Schluter Chapter 7, the hypothesis test. Okay, now, for the hypothesis test, I've got the basics laid out here. We're going to use the same exact four-part structure that we'll always use for hypothesis tests. So, first of all, null hypothesis. Doing the Whitlock-Schluter example, let's see, I've got that popped up here. A study of 25 genes involved in spermatogenesis found their locations in the mouse genome, and you can read the whole thing. I would like to just point out as we pass by here that they say it's testing a prediction of evolutionary theory that genes should occur disproportionately often on the X chromosome. That's interesting because according to evolution, I would predict pure randomness, and I would predict them to have the same proportions. Be that as it may, they're claiming that for evolution. On a design hypothesis, I might predict differences of proportions. So at minimum, this is simply neutral with respect to design versus evolutionary origin theories. So I really don't appreciate the way that's cashed out there. But at any rate, we're getting 10 out of 25, and the random prediction is 6.1%. So let's see how that looks on the hypothesis test. Okay, hypothesis test. Let's see here. We're going to predict randomness 0.061. That's the null hypothesis. That's the status quo. That's nothing happening. I've written that in words. The alternative then is going to be not 0.061. So null and alternative. That would be something happening. We're going to confirm at least our suspicion. Whether it confirms evolutionary theory or intelligent design is another matter, but at least it's there. Okay, now we need that test statistic. So in this case, we're looking at proportions, so my statistic is a p-hat. Okay, now underlying distributional theory is binomial. We have n equals 25 because we're looking at 25 genes, and the proportion then is 0.061. Where does that come from? Critically, it is assumed in my null hypothesis. That's where that comes from. Okay, so now we need a p-value. And we have a distribution. This is the null distribution. And it goes 0 to 25, although most of the bars are going to be over here. Let's see. So let's just call it that, but take a look at it on RStudio. And let's do n equals 25, p equals 0.061, and then I'm just going to call my good old formula that I did before, but I've put in n and p just to shortcut things. Now let's run the bar plot. Okay, I need out, and let's do 0 to n. Okay, figure margins too large. That's out 1. Okay, there it is. Now, we're predicting the 6%. In fact, we got 10 over 25, which is 40%. And so we actually got a 10 here. Now, how likely is it to get a 10 if this is the truth? Very, very unlikely. So what we want to do is compute the probability of that tail region. And that's the probability that we get 10 or more if this is the true distribution, which is very unlikely. Okay, so just to depict that over here, we'll go ahead and we'll put a 10 here. And that will be our p-value. That's that little tiny tail right here. Okay, p-value. So to calculate that p-value then, let's see, my p hat we need, that's going to be 10 over 25, which is the 40% that I've stated verbally. And so to get the 10 through 25, I'm just going to add those guys up, 10, 11, up through 25. And we can do that using R. The script is here. And so that pretty much gives it good to go. There's one little wrinkle, and that is I've got a 2 here. So where does this 2 come in? The 2 comes in from, it's called a two-tailed test. And it's allowing that we may be less than 0.061 or greater than 0.061. So we're going to consider this little region right here as well. And we estimate that by simply doubling one side. That's the technique the book says to do. And so that's what we're going to follow. All right, when we run that on R, we come up with 1.98 times 10 to the negative 6. You can tell that's a teeny weeny little value. So here's how we make the decision. It's always p-value versus alpha. So the p-value is 1.98 times 10 to the negative 6. It is way less than, let's just say 0.05, which is our alpha. That implies that we reject the null hypothesis. And so we conclude the true proportion of genes on the X chromosome is not the 0.061. In fact, it's greater than 0.061. Okay, and then I discuss about whether that confirms or disconfirms the evolutionary hypothesis. Now, to close out, I'd like to show you a single command on R which will do this. And we can go ahead and run it here on the software. It's called prop test, prop.test. And you put in your X. Okay, we had 10 in the observation. Put in our sample size N of 25, and then our probability P. The alternative is it's defaulted to be two-sided. I put it in there to show it. And what we're going to get out is a p-value. And you'll note that this differed from ours by actually a fair bit. So I want to just tell you that there's 3 different good ways to calculate this p-value. And so we used actually an exact way on one tail. When we double, then we're losing our exactness. There's 2 others, and they're using an approximation method here. So on R's prop.test, you will get some variation of your p-value. Don't be alarmed by that.